So thank you all for coming. Today I'm going to present you my PhD work regarding the development of a high repetition rate laser-wakefield accelerator that I conducted under the supervision of Dr. Jérôme Faure. So first question, why do we want to accelerate particles? Accelerated particles have many applications have many societal applications, such as in medicine when you're going for scanners or for radiotherapy. Also in industry for manufacturing some special components or for food sterilization via irradiation. If we go to proton acceleration, it can also be used to analyze and date some artifacts, as you can see here. But accelerated particles have also a big role still today in fundamental physics research. For low energy electrons, we can use them for doing electron microscopy. Or here you have a picture of a virus that has been taken using an electron microscope. Also for ultra-fast electron diffraction that I will talk about more later. Then if we go to higher energy, mega-electron volts to giga-electron volts, we can use those particles to create secondary light sources and create X-rays for imaging, for instance. And at very high energy, above 100 giga-electron volts, those particles are used to do some fundamental particle physics. Now the question is, how do we accelerate these particles? In all of my presentation from now, I will talk only about electrons. So the easiest way to accelerate particles is to use a linear accelerator. So you have a cavity, you apply a potential to this cavity, and this creates an electric field which is accelerating for electrons. Now, if you have an electron source, such as a cathode at the entrance of the cavity, some electrons are created at this cathode, and they will be accelerated by the accelerating field, and through acceleration they will gain some energy. But this way of accelerating electrons has two main limits. The first limit regards reaching high energies, because if we are in a cavity under vacuum, the accelerating field are limited to 10 to 100 megavolts per meters, which means that if we want to reach very high energy for particle physics, we need to use some huge facilities, because we cannot increase the accelerating field, so we increase the length of acceleration. Here you have two examples. The European EXFEL, which accelerates electrons up to 17.5 giga-electron volts within almost 2 kilometers. And the highest energy ever reached for electrons is 100 giga-electron volts at the LEP, which has not been replaced by the LHC, and which is 27 kilometers of circumference. So this is for the high energies. And now there is a low energy application, which is electron ultrafast diffraction, in which we need some very short electron bunch, and it's not possible to have such super short electron beams using linear acceleration. So the ultrafast electron diffraction principle is the following. We take an electron beam, we send it through a crystal, and it will diffract on the crystal. So we get the diffraction pattern after the crystal. And now if we use a laser to excite the crystal before the incoming electron bunch, then the electron bunch will see the excited crystal, and it will affect the diffraction pattern. So by monitoring the evolution of the diffraction pattern, we are able to monitor the motion of the atomic motion within the crystal in real time. And as in a camera with exposure time, the real time here is limited by the duration of the electron bunch. Using really continuous linear field, it's possible to accelerate electron bunch down to 300 femtosecond long. And now with some radio frequency field techniques, it's possible to create electron bunch with duration below 100 femtosecond, but with some shot-to-shot jitter between the electron bunches, which made us have some resolution still above 100 femtosecond. 100 femtosecond long for an electron bunch is already really good, but there are some phonons, so some vibrations of the crystal that have period below 100 femtoseconds, such as in graphene, where we have period of only 10 femtoseconds. So this was the two main limits of conventional acceleration, first getting to high energies, and then for low energy applications, getting short electron bunch. And now I will talk about an alternative way to accelerate electrons, which is laser-wakefield acceleration. In laser wakefield acceleration, laser wakefield acceleration was introduced by Tajima and Dawson in 1979. The idea is the following. So we have a plasma. So here, the violet stuff is a plasma. You take a short laser pulse, and we will monitor the movement of the electrons and the ions that are here in the plasma. So when we focus the laser pulse within the plasma, it creates a force, which is the ponderomotive force, that will expel the charged particles away from the region of high intensity. The ions are really heavy. They will see this force, but they will not be that much affected by the ponderomotive force, so they just pass straight through the laser pulse. But the electrons are much lighter, and they will really experience this force, and they will be expelled away from the region of high intensity of the laser. And then they will start to oscillate behind the laser pulse. So it results in this density distribution of the electrons. So we have a plasma with uniformly distributed ions, and the electrons who make this wake behind the laser pulse, with some cavities right behind the laser pulse, which is free of electrons. We only have ions, and the sheath of the cavities is made of electrons. So the sheath of the cavities being the violet here, made only of orange here, made only of electrons. So since we have some separation of charge, we have some creation of electric field, that we call the wake field, which is both accelerating and focusing for the electrons. If we place an electron within the bubbles, it will see this accelerating and focusing field, and we can accelerate the electrons. It's important to note here that we can reach really intense accelerating field in a plasma. We can go to gradients up to 100 gigavolts per meter, which is 4 orders of magnitude more than what we can achieve under vacuum. So now, just quickly, how it works, basically, laser wakefield acceleration. So we have a laser pulse, which is focused above a gas jet. The front of the laser pulse is intense enough, so front of the laser pulse here is intense enough to ionize the gas, so it results in a plasma. When the main laser pulse comes, it sees only a plasma. The laser wakefield acceleration process occurs, and the electrons are accelerated in the direction of the incoming laser pulse. Here you will see a small video of how it works within the plasma. So you have in green, it's the incoming laser pulse, which is focused in the plasma. And you will see in gray the electronic density in the plasma. So you see the wake is formed behind the laser pulse. And here in brown, you have some electrons that are injected in the bubble, and that then they are accelerated in the wake. So laser wakefield acceleration is a very promising technique for both of the limitations that we saw for conventional acceleration. First, we have very high gradients in the plasma, which means that we should be able to reach very high energies on very short distances. So this paves the way for compact acceleration. And then for the low energy applications, laser wakefield acceleration promised to create some electron bunch of only 5 to 10 femtosecond duration, which would be really interesting for increasing the resolution of ultra-fast electron diffraction experiments. So this is exactly the frame of my PhD. I worked with low energy electrons in view of doing electron diffraction. So I worked at the LOA in the APLI team, more precisely in the Saint-Laurent facility, and this team started with the objective of creating the mega electron volt femtosecond electron source using laser wakefield acceleration for ultra-fast electron diffraction applications. So this is exactly the goal of my PhD. And the parameters of the ideal source were determined by the first PhD students to work on the project in 2012. So if we want to achieve a time resolution about 10 femtosecond, we need some electrons with energy between 50 kiloelectron volts to 5 mega electron volts, with very low energy spread, quite high charge, low emittance, a very high repetition rate. This is really important for ultra-fast electron diffraction experiments, and a great stability of the electron beams. The state of the accelerator right before my PhD was the following. The laser-wakefield accelerator was working. We were able to get electrons on a daily basis with a very stable accelerator. So here you see an experiment that was running over 5 hours with 18 million shots, and you see the spectrum of the electrons during this whole experiment, which you see that it was very stable with no human interaction on it. But the electrons had energy still below 3 mega electron volts. So when I arrived, the objectives of my PhD were first of all to increase the energy of the accelerator, but with still keeping the stability of the accelerator and the kilohertz repetition rate operation. And also, once this should be achieved, another objective was to measure the emittance of the beam, like achieve low emittance beam and measure this low emittance, and then to perform some electron diffraction experiments on the Saint-Laurent accelerator. So this is the outline of my presentation today. First of all, I will quickly present you the specificities of the kilohertz regime and the Saint-Laurent facility on which I worked. Then I will present you a study we made regarding the influence of the gas species on the accelerator in view of increasing the electron energy. During my PhD, I also studied the CEP effects for laser-wakefield in the frame of laser-wakefield acceleration. I will not have time to talk about it today, but if you have any questions after, feel free to ask. And finally, I will present to you today an experiment of the measurement of the emittance of our electron beam in view of doing some electron diffraction. So first of all, regarding the kilohertz regime, well, for laser-wakefield acceleration in general, in order to reach this bubble regime, we need to have the laser pulse which is resonant with the plasma, meaning that the size of the laser pulse should be half of the plasma wavelength, the duration of the laser pulse should be half of the plasma wavelength as well. So this leads to some scaling laws that link the laser energy with with the duration of the laser and the plasma wavelengths needed, and that links also the another scaling law that links the plasma wavelengths with So there is another scaling law that links the plasma wavelengths, the duration of the laser, with the potential energy gain of the electrons that we accelerate. So with one Joule class laser system, in order to reach the bubble regime, we need 30 femtosecond laser pulses, and we can accelerate electrons up to the giga-electron volts level. And so in Saint-Laurent, we really want to work with a kilohertz laser-wakefield accelerator. So until recently, the laser systems that were able to produce the kilohertz pulses at kilohertz repetition rate were limited to a few millijoule per pulse. So with this energy, in order to reach the bubble regime, we need to use 3 femtosecond duration laser pulses, and we can accelerate electrons up to 10 mega electron volts. And this is the type of lasers that we work with in Saint-Laurent to do our experiments. So kilohertz laser-wakefield acceleration is possible to do with few millijoule, few femtosecond pulses. But in order to have the bubble regime, something which is really important is that we should work with very high densities, up to 10 to the 20 electrons per centimeter cube, and the acceleration occurs on very short distances. So this is for the kind of theoretical frame. Now I will present you more the experimental setup. This is the Salmoir laser system that I worked with, which is developed and maintained by the PCO group at LOA. This laser system is made of 2 principal bricks. The first one is Titan Sapphire CPA, double CPA laser that delivers 10 millijoule pulses at kilohertz with 26 femtosecond duration. This laser is focused within a hollow fiber here. Hollow fiber here that is filled with helium. In the fiber, there is a broadening of the spectrum. So here, you see the spectrum of the laser after the fiber. You see that the spectrum goes from 500 nanometers to 1,000 nanometers. So we have a very broad spectrum. And the laser is then sent to grating mirrors in order to compress the electron beam. And we reach this kind of temporal shape of the laser with a duration of 3.5 femtosecond, full width of maximum. The stability parameters of the laser are really, really good for all parameters, which are energy, beam pointing, or field jitter. And here you see a typical focal image of our electron beam, of our laser beam for doing laser wakefield acceleration. Now I will talk more about the Saint-Laurent accelerator itself. So as I told you, we have a few femtosecond, few millijoule pulse, which is focused down to a 5 micrometers focal spot with an off-axis parabola, meaning that we reach an intensity of 2×10⁻18 watt per centimeter squared. So the laser comes from salle noire, is focused by the off-axis parabola above the gas jet. The acceleration, laser wakefield acceleration process occurs here, and the electrons are sent to our diagnostics. So we have a scintillator and a motorized spectrometer so that we are able to monitor the beam profile, the beam charge, and the electron energy. Sorry, I hope noise is okay. So now, something to note also is that since we are working at kilohertz, the gas jet that we use must be a free-flowing gas jet in order to handle the kilohertz operation. Ah oui, merci. Yeah, to handle the kilohertz operation. So we have a free-flowing gas jet, which will be really important later. A lot of work has already been done on this accelerator. So here you see all the papers that have been published by the former PhD students and postdocs that worked on the accelerator. And now here are some few pictures of the accelerator. So here it's the salle noire laser system. So on the left, here you see a picture of the whole room salle noire. The laser takes all of this place here. Here on the right, you see a picture of the hollow fiber, and the orangish light that you see is the light of the laser after propagation through the fiber, so once the spectrum is already really broad. Now here is the experimental setup. So here it's the experimental chamber in which we did the experiments. The laser comes here from salle noire. It is brought down in our chamber. Then inside the chamber, the laser is focused by the off-axis parabola above the gas jet, which is in this little box here, and then the electrons are sent to our diagnostics. A few words about how we inject electrons. So I will present you only one mechanism of electron injection, which is injection in a density down ramp, because all the results I will present you today were made using this type of injection. So the gas jets that we are using are of this typical form. It's a micrometric gas jet that are specially designed so that there is a small wall here, and the gas that comes from the gas jet reflects slightly here on the wall. If we take a line out of the density on the laser propagation axis, you have this density profile, and you see here what we call the down ramp. And in fact, as I told you earlier, the plasma wavelength is directly linked to the electronic density. So when we have a certain electronic density here, we have a certain size of the plasma bubble. Then in the density down ramp, the bubble is getting bigger until it reaches its final size here at the last point. So you see that the electrons that were first at the back of the bubble are not trapped inside the bubble, and we can say that we have injected the electrons. So this was for the presentation of the setup. Now I will move on to the first big experiment I did during my PhD, which is the study of the influence of the gas species on the accelerator performances. Why did we want to test new gases to get higher energies? In fact, so here it's the same result as I showed you before. It's the stability of our accelerator with the former PhD student. So with this result, we had very stable electron beam at kilohertz repetition rate, but below 3 MeV, and using a nitrogen plasma. But in 2021, there is another group in University of Maryland who managed to create electrons up to 15 MeV using laser parameters that were similar to ours, but they were working in burst regime, not in continuous kilohertz operation. and they were using a plasma made of hydrogen. So we wanted to test different gases and to see if we can really achieve better energies with different gases. So first of all, why do we use nitrogen? It's because using nitrogen, our laser is intense enough to ionize the 5 first level of nitrogen, which means that we really quickly reaches the electronic density that we need. But as you can see, so we have 5 different energy levels. And so the molecule of nitrogen, when they will see the incoming laser pulse, depending on their position with respect to the laser axis, they will not see the same laser intensity. So they will not be ionized up to the same level, meaning that we have an electronic density which is non-uniform, and the refractive index of the plasma is directly linked to the electronic density. So if we have this type of electronic density distribution, in fact, the plasma acts as a defocusing lens, which damages the plasma at the laser at focus, and which may so reduce the performance of our accelerator. So we want to go for lighter gases, such as helium and hydrogen, which have only 1 and 2 electronic levels. But the problem is that, so as I told you, when we used, so we need very high electronic density. When we use nitrogen, each molecule of nitrogen ionized provides 10 electrons. So we only need 20 to 30 bars of gas, of backing pressure in our gas jet to reach the electronic density that we need. And if we want to work with helium or hydrogen, those 2 molecules provide only 2 electrons per molecule, which means that if we want to reach the electronic densities required for experiments, we have to work with 100 to 150 bars of gas in our gas jet. So this is already a much more important amount of gas which is sent into the experimental chamber. And also, lighter gases are harder to pump than heavy gases. So it's harder to pump helium and hydrogen than to pump nitrogen. So in order to do this experiment, we had to implement some differential pumping within our experimental chamber. So what is the differential pumping system? So we have our main experimental chamber. The gas jet is in the middle of the chamber. And what we do is that we put a small box, so a second chamber, around the gas jet. So here you have a 3D view from the outside with the gas jet inside and the small chamber around. There are 2 holes in this chamber to let the laser in and let the electrons out. And there is a pipe just above the gas jet with a pump which is plugged here to evacuate the gas. So here you have a picture of the setup in the experimental room. Just few pictures of the pump. So our experimental chamber here was pumped by a root pump and a turbomolecular pump. Do you still hear me? You do? Allô? Yeah. Ouais, je pense. Okay, ici, is it okay? Okay. So we have the so 2 pumps, 1 root pump and 1 turbomolecular pump to pump the experimental chamber, and the small differential chamber is pumped by these 2 pumps that you see here. So 2 huge pumps just for the experimental chamber, for the differential chamber, sorry. Now about experimental results. So we monitored the pressure in the experimental chamber versus the backing pressures that we put in our gas jet. First we did that without differential pumping, so only the free-flowing gas jet in the experimental chamber. And you see that using nitrogen, the pumps are quite, can handle the amount of gas that is sent in the experimental chamber, so the rise of the pressure in the chamber is still manageable, especially if you consider that we are working only with 20 to 30 bar of nitrogen, so we remain here with a pressure which is good enough for doing the laser-wakefield acceleration experiments. And then when we try to switch to helium, you see that even at low pressure, the pressure in the low backing pressure, the pressure in the experimental chamber is much higher than using nitrogen, and it rises very quickly. The pumps are not able to handle those amount of hydrogen, of helium in the experimental chamber. And now, if we repeat the experiment with differential pumping, you see that even with 140 bar of hydrogen, we keep a pressure in the experimental chamber which is below 310 to the minus 4 millibar millibar, so which is really enough for doing our electron acceleration experiments. A question that may arise with differential pumping system is there some stagnation of the gas in the small chamber around the gas jet? And if yes, does the stagnation of gas will have an impact on the propagation of the laser pulse up to the gas jet? So we conducted some fluid simulation using the software ENSTA-PARIS, really to simulate how the gas was evolving within the chamber. And here you see the result of the simulation. And you see that we have the gas which is well confined within the chamber, with some gas here still around the gas jet. And now, if we take a line out of the gas density on the laser propagation axis, this is the line out that we have. So here in the middle, we have a peak of density which corresponds to the gas jet, so which corresponds to the plasma we will have for doing laser wakefield acceleration. And then here you see that there is a small plateau with a length of around 3 millimeters in which the laser will propagate. So the question is, does this have an impact on the laser propagation? So to estimate the impact, we did some simulations using the AXIPROP library with parameters similar to our experimental parameters, and we monitored the intensity and the spectrum of the laser along propagation. So here you have the intensity of the laser around propagation. You see that the intensity is really slightly reduced. And if we look at the spectrum is barely modified. So the laser is not that much modified, and we should still be able to do our experiments even with this small amount of gas in the chamber. So we did the experiments. Here are the results. So you have on the left the beam profiles of electrons accelerated with different gases. So the first line is for hydrogen, the second for helium, and the last one for nitrogen. And we also tested different configurations with different electronic densities. So at first sight, what you see is that using hydrogen, we have much smaller electron beams. Especially if you are looking around here, electron beams are really much smaller using hydrogen. Using helium and nitrogen, we have beam profiles that look kind of similar. And regarding the charge, we have a charge which is higher using hydrogen if we look here. Now, if we look at the energy of the electrons, especially for this specific density, here you have the spectrum of the electrons for the three gases. In green, it's for hydrogen, in orange, it's for helium, and in blue, for nitrogen. And you see once again that hydrogen clearly stands out with a peak energy at 7 MeV, while using helium and nitrogen, we do not overpass 4 megaelectronvolts. So from our experiments, we clearly concluded that experimentally hydrogen overpass other gases with higher energy, higher charge, and a better beam profile. Now we wanted to explain why we had these results. So we did some FBPIC simulations to really reproduce what was happening in other experiments. We used some parameters, the parameters of the experiment. So laser parameters correspond to the parameters of the laser in the experiment. And for the density profile, we used a density profile that was measured with the gas jet similar to the one used in the experiment. Here you see the beam profile of the electrons in the simulations for different gases. So first line for hydrogen, then helium, and finally nitrogen. Once again, you see that we have a beam profile which is better defined using hydrogen than using the two other gases, and we have higher energies using hydrogen, and we have higher charge using hydrogen. Now, if we look at the spectrum, we have higher energies also in hydrogen, which is the green line, and nitrogen in blue and helium in orange, have energies that are less important than using hydrogen. So these simulations results reproduced the trends that we observed in the experiments with hydrogen, which was always standing out from the other gases. So we used these simulations to really understand what was going on during the acceleration process. So first, here on the left, you see the evolution of the laser normalized intensity along propagation. The gray areas that you see here corresponds to the electronic density within the plasma, so it's the density profile in the plasma. And you see, so the intensity for the three gases, helium, hydrogen in green, helium in orange, and nitrogen in blue. And in red, it's the normalized intensity for the laser propagating in vacuum, just for reference. So you see that using hydrogen, we reach a higher intensity than using the other gases, and helium and nitrogen have very similar behavior. We can also have a look to the spatiospectral spectrum of the laser. So here you see the spatially resolved spectrum at this position. So electrons have already been injected, acceleration already started. And you see it for the three gases, hydrogen, helium, and nitrogen. And two things appear in helium and nitrogen that do not appear in hydrogen. First of all, there is a transverse broadening of the laser pulse in helium and nitrogen. So here in hydrogen, you do not have this broadening at all. And also here on the right, you see that there is a blue shift of the spectrum using helium and nitrogen, blue shift that doesn't appear here in nitrogen. We can also have a look at the wake field during the simulation. So this is a wake field picture at the same instant as the spectrum I just showed you. First line for the wake field in hydrogen, then in helium, and finally in nitrogen. In orange, you have the laser pulse intensity. In green, it's the electronic density distribution. And in brown, it's the electrons that are injected with the vertical coordinate corresponding to the longitudinal momenta of the electrons. So you see that using hydrogen, when the laser pulse was focused with higher intensity, it drives a wake field which is more intense, and it managed to trap the electrons right behind the gas jet, with electrons trapped only in the third bubble after the gas jet. And you see that they are accelerated within this bubble. Now in helium and nitrogen, the electrons are injected in bubbles much further away from the laser pulse. So the laser pulse excited by the laser was less intense. It was not able to trap electrons right behind the laser pulse. But the further we are going away from the laser, the slower is the wake field. When the wake field slows down, it's able to trap electrons. Electrons are trapped here and are slightly accelerated, but they will experience less intense accelerating fields. This is why we have more energy using hydrogen than using helium or nitrogen. Here it's just for your just a schematic, just to explain why we have similar results in nitrogen and helium. So you have the intensity of a laser pulse against time for a perfectly Gaussian laser pulse, and I draw the ionization levels of all the gas that we use. You see that hydrogen is ionized really in the pedestal of the laser, so it will barely affect the laser pulse. But helium and nitrogen, they will be fully ionized quite close to the laser intensity, especially, and for helium, especially the second level is really close to the fourth and fifth level of nitrogen. And thus, this will have a more intense impact on the laser pulse, and this explains why we have similar results in helium and nitrogen. Then we also kept going with the experiment, and here I will just show you one of the best results that we got during our experiments. So here you have a video of an electron beam. So each picture is a single shot of electron beam, and here you have 100 shots that are shown on the video. And this was obtained using hydrogen plasma with very, very stable parameters, whatever parameter we are regarding, energy spread, charge, beam pointing. Everything is very stable RMS with a beam pointing stability of only 1.5 milliradian RMS. And in the field of laser wake field acceleration, this is one of the best, most stable beams that we got. And this concludes my first part regarding the study of the influence of the gas pulses on the electron beam. Just a few words, we didn't just change the bottle and change nitrogen to hydrogen. This was quite complicated to do, firstly because hydrogen is an explosive gas, so dangerous to handle. We had some problems with the laser, we had problems with the pumping systems, with the gas jet, which had to handle very high pressure, and also since we are going to high energies, we were irradiating everywhere in the lab, so we had to be careful with irradiation as well. Now I will go to the second main results I want to present you today, which is the measurement of the emittance of our electron beam in view of doing electron diffraction. So the idea is the question that rises here is, can we fully describe an electron beam? If I reduce the electron beam I just showed you, here we have 2 picocoulomb electron beam, which corresponds to 10 to the 7 particles. Each of these particles has 6 coordinates of position of momenta. So it's not possible to describe the electron beam by describing each particles one by one, and we have to go for a more statistical description. The statistical description is the emittance, and specifically here we measure the geometrical emittance. Just to have a better view, a better understanding of what's going on, you have your electron beam, which in real space has a certain size x and divergence x prime. And if you draw your electron beam in the phase space, you can also draw an ellipse around the electron beam, and the area of this ellipse is linked to the geometrical emittance of the beam. Something which is really important is that the geometrical emittance is conserved in linear beam transport for the electrons. And the smaller the emittance is, the better the quality of the beam is. If you have emittance of 0, you can infinitely focus your electron beam. Now, if you want to send your electron beam through accelerating and change the energy of your electron beam, the parameters that will be used is the normalized emittance that normalizes the geometrical emittance with the energy of the electron beam. So now just quickly I will show you the principle of the measurement of the emittance. Just what you have to know is that the size of the beam is function of the emittance of the beam and other parameters. So what we do is that we have a beam which is created here at the 0 point. We will propagate it on a certain distance delta, then it will see a focusing component, which is a solenoid, which has a certain magnetic field and length, and then we propagate again the electron beam, and it's focused on a screen. If we move the position of the solenoid, the focal position will change. So if we keep the screen at the same place, we will see a beam which is out of focus, getting focused, and then out of focus again. And then we can use this curve to find epsilon, because it's possible to do some simulations of the trajectory of the electron beam in the magnetic line, and to fit the simulations with the sigma curve. Now how the experiment itself, so as I showed you, we have the acceleration, so laser which is focused above the gas jet, laser-wakefield acceleration process that occurs here. Electrons are accelerated, they are sent through the solenoid, and then they are focused on a gag crystal. The typical electron beams that we had during this experiment had this beam profile with this type of energy, so peaked at 2 mega electron volts. And the beam was focused. Here is one of the focus that we have with the solenoid. Again, this was not just putting a solenoid in our experimental chamber, because the solenoid was really this size, and everything was really tight in the chamber. So here was a chamber before doing the experiment. We had to remove everything, almost, and then put back everything, doing small Tetris to be able to put the solenoid. And here you see a picture of the solenoid, which is really, really close to the gas jet, as close as possible. Now, something to say is that the solenoid is a really chromatic device, and here you have the equivalent focal length of the solenoid, you see, which is really strongly depending on the electron energy. So if we look at the trajectory of electrons with different energy being focused, you see that different energy are focused really in different places. And our electron beam is not monoenergetic. Here you see the spectrum of our electron beam. We have very various energies. It means that so the sigma curves that we have, if we have a monoenergetic beam, is the blue curve that you see here. And if we have a Gaussian distributed spectrum, it becomes the orange curve that is here. And this orange curve is not exploitable to find back the emittance. So a little trick is to insert a dipole in the electron beam path. So we have our solenoid, the screen, which is a few tens of centimeters away, and the magnetic dipole, which is placed in between. The dipole will disperse the energy. It will disperse more the lower energies, and more the lower energies, and the higher energies will be less dispersed. And so if we look at the screen, each position on the screen will correspond to one specific energy. So we will have this type of butterfly shape with a pinch here for the energy which is focused. When the solenoid is moved, different energy will be focused on the screen. So in fact, in the experiment, we will see the pinch of the butterflies that will move transversely. And if we use this trick and we select only one specific energy, then we have this green curve here. So we just take one line, one specific energy. We got this green curve, which is usable for finding back the emittance. Now for the experimental data. So I will show you the experimental data. Here on the left, you have a picture of the screen. So you see the butterfly, and in orange, it's the energies that we choose to evaluate. So you have here in orange the line out of the energy, and we measure the size of the transversal size of the electron beam for this specific energy. And if we move the solenoid, we see that the pinch of the butterfly is moving. You see that for one specific energy, we are getting to a very thin electron beam, and then out of focus, it's getting bigger again. And we got the sigma of a delta curve again. So now to fit this data with simulations, we use the code General Particle Tracker by Pulse of Physics. This code allows to trace the trajectory of electrons. I don't know if you hear. Allô. Ouais. J'essaye avec un des grands peut-être. Bon, là ça va. Ouais. Là ça marche. So this code allows us to trace the trajectory of electrons within a magnetic line. So we initialize the code with a spatial distribution, which is Gaussian, and a spectral distribution, which is Gaussian, and which are similar to the ones that we measured experimentally. And then we placed in the code the 3D maps that were of all the components used in the line. Those maps were simulated using the software Pulse of Physics, and we explored a certain range of parameters. Here you see a typical simulated spectrum, simulated screen using GPT. So we see again the kind of butterfly shape. And now here you see how the curves, sigma over the versus delta curves evolves when we are changing parameters. If we are keeping the same size of the initial beam but changing the emittance, it's the slope of the curves that will change. And if we are changing the initial size of the beam but keeping the emittance similar, it's the size of the image that will change. So we tested various parameters, and you see that there is one specific parameter that fits our experimental data. So here it's the best fit that we have, which corresponds to an emittance, geometrical emittance of 20 nanometers radians, which is also 124 micrometers milliradians if we look at the normalized emittance. And here the blue uncertainties corresponds to the resolution of our optical system. So we were very happy to first be able to measure an emittance, and then we compared this emittance with emittance of various accelerators in the world. And if we look especially at our range of energy, so below 10 mega electron volts, you see that here we are in red. In blue, it's all conventional accelerators. Laser-wakefield accelerators are in orange, not in the same range of energy. And so we have a normalized emittance, which is really comparable to the one measured in conventional accelerators. And we can also have a look at the charge of our beams. So we have some reduction of the charge by measuring the emittance because of the pinhole in the setup. And you see that still our charge is comparable to the one used in conventional accelerators. So this was really encouraging for doing some electron diffraction experiment. So we really moved to this experiment. We placed a sample right after the solenoid. The sample is a silicon sample, monocrystalline, with 78 nanometers of thickness. And then in order to be able to resolve the diffraction peaks of the electron beam, we placed the scintillator 2.6 meters away from the sample. So here you see the solenoid with the sample holder here, a picture of the sample which is here, and here you see the 2.6 meter pipes that was added to the experimental chamber. And we managed to have a focal spot on our scintillator that you see here on the left. And when we placed the sample in the electron beam path, we managed to have an electron diffraction pattern with several peaks, with still good intensity. So we were very happy to have this kind of image. It was the first time that we got a diffraction image in Saint-Laurent. And we were not able to measure the electron spectrum during the experiment at this time because of all the it was not so possible to have the sample and the spectrum at the same time. But by measuring the distance of the peaks, we estimate that the energy of the electron, which is diffracted here, is 500 kiloelectron volts, which is, from what we know, the state of the art of electron diffraction with laser-wakefield acceleration, with electrons accelerated through laser-wakefield acceleration. So something we still have to keep in mind, thus, is the idea in Saint-Laurent was really to create an electron bunch with very short duration. Here we estimated that the duration of our electron beam at the sample position should be around 45 picosecond, which is still huge, because of the fact that we have only 500 kiloelectron volts and a high energy spread. If we manage to combine everything that we did during my PhD, so getting to high energies, if we manage to select one specific energy, we should be able to go down to a duration of 89 femtoseconds. So there is still areas for work for improving this in Saint-Laurent. Also, the focus you see here still has some aberrations that have to be worked on. And just in comparison, conventional accelerators also made some progress during all this time, and now they are able to reach electron beams with duration as short as 6 femtosecond RMS, and even using some radio frequency techniques, they have some electron bunch with duration of 25 femtosecond RMS, but with a very low shot-to-shot jitter, meaning that they can achieve resolution of only 30 femtosecond. So we have a lot of work if we want to catch up with them. So this brings me to the conclusion. So first of all, we have in Saint-Laurent a consistent and reproducible control of the Kilohertz laser-wakefield accelerator. During my PhD, we significantly improved the beam quality. Using hydrogen, we got higher charge, better beam profile, and higher energies. And we were able to measure a normalized emittance of only 124 micrometers milliradians, which is comparable with conventional accelerators. And we made the first experiment of electron diffraction in Saint-Laurent. So just quickly, what's next for the appli team? Now the team will move to applications with higher energy for the electrons. They plan to do an X-ray source via Compton scattering, or to do some radiobiology experiments, and they're working on the Laplace facility, which aims at delivering electrons with 100 megaelectron volts at 100 hertz. And they have a lot of work to do, and they will, I hope, fulfill to have electrons really quickly. And then I want to take some time to thank all the people I worked with. So first, all the people from the Saint-Laurent team, appli team, who worked on the accelerator with me. Then the people from Salnois who really worked on the laser and who allowed me to have all the results I showed you today, even though they also had their PhD to do in the meantime. Special thanks also for the workshop, who was really reactive when I was making all my pieces, and for making, for everything. Thank you. The secretariat was really helpful also. All the collaborators from Lithuania who do manufactures gas jets that are very particular. And then all the people I interacted with during my PhD. It was a pleasure. And thank you to all of you. If you have any question, I will be happy to answer.